In this module, we'll begin our tour of functional groups, which are basically the way that molecules recognize one another and ultimately chemically react. Our learning goals for this video will be to define the structure of hydrocarbons and halides, which will be the first functional group. We'll also look at how intermolecular forces affect physical and chemical properties of these molecules. So let's get started. First, let's recognize that intermolecular interactions generally arise from the forces that are coming from the partial charges on molecules. This is how they recognize one another. So this affects not only their collective physical properties, including things like their melting point and boiling point, but also it affects how they interact and undergo chemical change. So the whole process of making and breaking bonds, this is how they recognize each other and how they react. So functional groups represent particular bonding patterns that set up a charge distribution within a molecule, and that charge distribution becomes something that gives it a fingerprint, if you will, with other molecules. These determine the molecule's chemical properties, and that's why we care about these different functional groups. So we're going to start with basically our baseline. These are the things on which all functional groups are built, and that is the hydrocarbons. These are the molecules that contain only carbon and hydrogen. So they include things like the alkanes, which have only single bonds, the alkenes, which have at least one double bond, and the alkynes, which have at least one triple bond. There are many possible ways we can make these. We can have linear chains, we can have branch chains that have branches that come off of a linear chain. This is an example of 2,2,4-trimethylpentane, which you might recall from an earlier video. We can also have cyclic molecules, and we can have fused rings. So there's a whole variety of different hydrocarbons we can have, and this is what gives such a richness to the array of carbon framework molecules that we're studying in this course. Hydrocarbons are noted for having nonpolar covalent bonds. That is to say, carbon and hydrogen have about the same electronegativity, so they don't generate polar bonds, and their molecules, hydrocarbons, are typically nonpolar. They have relatively weak intermolecular forces. So this means that the smaller ones are gases at room temperature, and the medium ones are liquids, and it's only the larger ones that become solids at room temperature. Carbon-carbon and carbon-hydrogen bonds are very strong. They range from about 350 to 420 kilojoules per mole, so these are not molecules that fall apart very easily, and they're stable up to high temperature. Now I've shown you a chart here of the boiling point of linear alkanes, and you can see that as they get longer, their boiling point goes up. That tells us that the intermolecular forces between these alkanes get stronger as they get longer. Okay, the progression is pretty regular, so it becomes actually a very predictable thing, and one can use a chart like this in some cases to, if you measure the boiling point of an alkane, you could correlate that with the number of carbons, so you could identify the alkane from that. The chemical properties are pretty specific to hydrocarbons. Of course, they all combust. We're used to burning gasoline. What happens during combustion is basically it replaces the carbon-hydrogen bonds with carbon-oxygen double bonds. That is to say, they create CO2. In this case, carbon loses electron density. It becomes oxidized. And the reaction generates a lot of heat. We're used to things burning. They generate heat. This is how we heat our homes when we burn natural gas. They have free radical reactions, which we'll talk about later in the course. They are the starting material for industrial products and pharmaceuticals, and they're found in petroleum and natural gas. So I mentioned earlier burning natural gas to heat our homes. We also use it to cook, and here's an example of that. Let's move on to halogens. Halogens occur when we incorporate these molecules, these atoms, these elements in the halogen column of the periodic table into these hydrocarbons. That includes fluorine, chlorine, bromine, and iodine. We usually don't see molecules with astatine or element number 117 very much, so we'll focus on those first four. Their bonding capacity is 1, which is the same as hydrogen, which means they're basically going to replace hydrogen in the hydrocarbons. They increase in size as we move down. Remember, they're getting larger and larger orbitals, so the size increases of these atoms. And that actually is important in terms of how it affects their chemical and physical properties. their electronegativity increases, and that is also important. All of these are more electronegative elements, so they tend to carry a negative charge, partial charge, when they are on a hydrocarbon molecule. So let's take a look at some of these. So as I mentioned, halogens replace hydrogen in hydrocarbons. Here's an example of a large hydrocarbon with chlorines on it. This is actually DDT, an insecticide, which now is not favored for use, shall we say, because it causes neurological damage in the environment, but nevertheless was used for quite some time. It features polar bonds. These are the carbon-halogen bonds, which I'll call CX. X will represent halogen in all of these. So these are polar bonds that create a partial charge distribution in the molecule. They tend to be weaker than the carbon-hydrogen bonds, except for the carbon-fluorine bond, which is a very strong bond. So these, because they're weaker, they are sites for subsequent reactions. So this is their first clue that having functional groups does partially dictate the chemical properties of these molecules. They have much stronger intramolecular forces because they have this partial charge, and those forces increase with the size of the halogen. Okay, this is actually not so much due to the electrostatic force as much as it's due to something called a dispersion force. These are all polar bonds, and here's a table that indicates what some of their properties are. What I've drawn here is the methyl halide for each of the fluorine, chlorine, bromine, and iodine varieties. And we can take a look at how they compare with one another. We can see that in terms of their size, and this is moving across from left to right in the first row, their size increases as we move from fluorine to iodine. Okay, well, that's natural because iodine is the largest of these four and fluorine is the smallest. Their strength, though, decreases, and this is another reminder that the longer a bond is, the weaker it tends to be. Iodine is very large, so it can't make a very short bond with carbon. Dipole moment is variable, and this is actually kind of an interesting one. The first three are all pretty comparable. The last one is smaller. Remember, the dipole moment is the charge separation times the length of the bond. The bond is getting longer in each of these cases, so it tells us that the charge separation is actually getting smaller. We're getting less electronegativity in those halogens, so they're not separating charge as much. They're compensating with that by having longer bond length, and that's what keeps the first three relatively constant. By the time we get to iodine, it really is not as electronegative, so it doesn't separate charge so much. So a lot of the contribution for its dipole moment is coming from the fact that it has a long bond. The vaporization temperature, however, is increasing in all of these, so that's telling us that the intermolecular forces are getting stronger as we move from methyl fluoride to methyl iodide. Let's take a look at what these look like. Here are some MEP surfaces for each of them, and you can clearly see that the bond is getting longer as we move across, but you can also see that the intensity of the charge separation is greatest for the methyl fluoride, and it decreases as we move across. So this confirms that the dipole moment is being preserved in the first three largely because the bond is getting longer, not because it is separating the charge any differently. It's actually separating the charge weaker. So this has been our introduction to halides. We'll move on to some other functional groups in subsequent videos.